So 12.2 is the counting outcomes and tree diagrams. So kind of drawing pictures to see what the answer is going to be. So if a recipe calls for 4 ingredients: flour, baking powder, shortening, and milk, we're just going to use the F, the B, the S, and the M. But there are no directions stating the order in which they should be combined. Chris has never followed a recipe like this before and has no idea which order is best. So he chooses the order at random. So what's going to happen here is how many different possible orders are there? So a lot of times we'll just put the 4 blanks down. And then if you're going to put one ingredient in, the very first ingredient, how many choices do you have? How many choices do you have?
4.
You have 4. So we go 4. But once you've emptied one of the ingredients in a bowl, how many choices do you have for this one?
3.
Only 3. And then 2. And then 1.
It leads us to the fact we can also figure out by a function called x factorial. You can just go to math, go to PRB, and you should see a 4 exclamation mark. It's really x factorial, and you can do that for your answers, and you get 24.
24. Yes. So 4 times 3 times 2 times 1 is the same as factorial. You can do that on your calculator. You can find it here. So you type in the number 4, you can hit math, slide over to the PRB, which is the probability menu, and you'll see the exclamation point is number 4, so 4 exclamation point, hit enter and you get 24. Same as 4 times 3 times 2 times 1. Now, what is the probability that milk should be first? So we have the same type of problem, but in this case they're telling us that milk has to go first. So how many choices do you have for the first ingredient? 1. Now, they don't care what ingredient you use next, so then that one's 3, 2, 1 like this. So multiplying by 1 doesn't change it, so then times 3 is 3, times 2 is 6. And so you end up with 6 different choices. Now, what's the difference between question A and question B? They didn't want to know how many ways, right? They want to know probability. So if they ask us for probability, what we have to do, probability is always part divided by the whole. So if there are 24 different ways to put your ingredients in there, and there are 6 ways to do it with milk first, you have to make sure you're doing 6 divided by 24, which is 1/4 reduced fraction, or 0.25. Which probably makes sense. 4 ingredients, if you have to put one of them first, there's a 25% chance that that's the way it's going to be. So what I'd like you to do is go through C, D, and E on your own. Write those answers in for C, D, and E, and then we'll come back and I'll put the answers up there. Look. So what is the probability? Again, they're not asking for how many, they're asking for probability. So you have to take whatever you find and divide by the 24. So we could put our 4 blanks down. And in this case, it includes flour first. How many ways can flour go first? 1. How many ways can shortening go second? 1, which leaves you with 2 choices there, and then only 1 choice there. So 1 times 1 times 2 times 1, there are only 2 ways that this can happen. But it's probability, so we have to take the 2 over 24, which reduces to 1/12, and 1 divided by 12 is
0.083.
0.083, repeating, so about 8%. What is the probability that the order goes, specifically F? So flour, baking powder, sugar, milk, I don't even know what they were. So a very specific order. How many ways can it be in that order? One way. This only happened one way. So this is 1 out of 24, which is
0.416 repeating. 0.0416.
0.0416 repeating, something like that. Good. What is the probability that the order isn't that? So the what? The complement they're talking about. Everything else, right? The not. So you have this, there are two parts. So if it's 1 out of 24, then the probability that it isn't in that order, there are 23 ways. So 23 divided by 24 is 0.958, whatever, something like this. So that's called the complement. In 1963, the U.S. Postal Service introduced the zip code to help process mail more efficiently. So instead of saying, mail my letter to Minneapolis, Minnesota, cities were getting large enough that they needed to have more specific locations. And so a zip code contains 5 digits, 0 to 9. How many possible zip codes are there? So how many zip codes can we make? Well, how many choices do I have for the first number? 0 to 9 is how many? There are 10 choices. 1 through 9, but the 0 is first, so there's 10 choices. So it's 10 for that number, 10 for that, 10 for that, 10 for that, 10 for that. Or 10 to the 5th power, right?
Equals 100,000.
So we have 100,000 different zip codes we can use in the United States. In 1983, the U.S. Postal Service introduced zip plus 4. The extra 4 digits at the end of the zip code help pinpoint the destination of a parcel with greater accuracy and efficiency. How many possible zip plus 4 zip codes are? So in other words, now you take a city like Minnetonka and you have 50 or 60,000 people that live here. Now you can split it up into maybe quadrants. So the plus 4 part helps kind of pinpoint that area. So you still have your 10 to the 5th power, right? Now what are you adding behind it? Right, so now you're multiplying by an additional 4 more 10s, right? So really what you end up with is 10 to the 9th. So that's 1, 2, 3, 4. And what's that number?
1 billion.
1 billion. You should do this, we said. All right. So that's a ton of different combinations. The Canadian Postal Service uses a 6-character mailing code in the form of letter, digit, letter, digit, letter, digit. How many possible Canadian postal codes are there if no restrictions are placed on their code? So, if it starts with a letter, how many choices do you have for the first position? 26. So 26 letters in our alphabet. Then the next is a digit. So that's a 10. Then a 26. Then a 10. Then a 26. Then a 10. Now you can write that out. You could do 26 cubed times 10 cubed. Whatever you want. What do we end up getting?
$17,576,000.
Hang on. 17,576,000.
576,000.
Thank you. So their basic zip code that they use compared to our basic zip code, by using letters, you know, we only have 100,000 combinations with our system, and they would have 17 million combinations. In Canadian postal codes, the letters D, F, I, O, and Q and U are never used. And the letters W and Z are not used as the first characters. How many possible postal codes are there now? So I'm going to pause the video. You're going to write that out. And then we'll come back and take a look at the answer. Okay. So as far as my digits go, I still have a 10, a 10, and a 10 for my choices when I do my digits. But with the letters, we have to be a little bit more careful. There are 1, 2, 3, 4, 5, 6 letters that can't be used ever. So in this position, this particular would be 26 minus the 6, right?
20.
So I can use 20 there. I can use 20 there. But in addition to those 6 in the first position, for whatever reason, we can't use W and Z. So now there's really 8 numbers, or 8 letters that I can't use. And so that's an 18. So did somebody multiply that out?
That's 7,200,000.
7,200,000, thank you. Any questions?